Greetings. I am Professor Frederic for Leymarie, speaking from London. I seek to better understand what makes us human, a special species. I have long studied how we perceive and make sense of the world by our visual capacities. I test hypotheses with algorithms, software, and robotics. More on this later on. I wish to thank for this opportunity to participate with you, the Chinese Calligraphers Association, Capital Normal University, the Research Institute of Chinese Calligraphy, Culture, and the Sino-Foreign Calligraphy Research Center of Capital Normal University. And special thanks to Professor Xuefeng Sun. My talk is entitled A.I.M, Art.Intelligence.Machine, which stands for my current main research agenda. The aim is to deepen our understanding of the close relationship existing between human art and human-made machines and tools, and what makes us intelligent beyond what other species can achieve. In this short first part, I want to give an overall motivation for my research program. In a second part, we'll focus on recent research relevant to calligraphy. I study art, and by that I mean aspects of perception, making of art, and the practice of art, together with artists and other scientists. I conceive of art as a special domain to study, to reveal specific human traits. I will also relate to the use and making of tools and machines, and how together they deepen our study of human intelligence. Why art, you may ask? Art is a human activity since the origin of Homo sapiens. Art, in fact, precedes and leads to the invention of other human intellectual activities, including writing, arithmetic, mathematics. It sits at the origin of symbolic thinking and communicating. Humans' fascination for patterns, graphical representations, can be traced back tens of thousands of years. The use and the evolution of graphical symbols is universal across cultures and geography. The development of visual symbolic patterns is at the root of the emergence of written language. I conceive of art as one of the few necessary and distinctive traits that explains humans' extraordinary cognitive capacities amongst all species. The other traits which I think explain Homo sapiens' specific capacities are tool and machine making, thanks to our dexterity, and complex communication, including via language. Let me say a few words on how I consider the study of intelligence in humans. I propose to focus on those activities which are not present in other species, or not to any significant degree. In short, at the origin of Homo sapiens, these include art, the making, the practicing, the refining, but also machines, the invention and making and refining of tools, more and more complex, leading to powered machines, later to computers, robots, and language, including the written, to permit the comprehension and exchange of abstract ideas among people and cultures. But I think the real power of these human traits is, once combined, to allow us to keep advancing as societies, because together they permit to us to archive knowledge, pass it on to the next generation, keep refining it, and this is truly unique to humans on this planet. How I, as a computer scientist, see the role of AI in this perspective on human intelligence. AI can be a field focused on the study and understanding of what makes us different. This is a message. AI can and will also serve to extend our cognitive horizons, as art and machine do. So moving on to part 2, the research aspect, concrete research. There is, of course, a longer story to tell about motivation and the A.I.M agenda. But that will be for another talk. I will focus on a recent set of works established with a number of close collaborators, and in particular with one of my PhD students, Daniel Berriot, an artist, scientist, engineer. Following earlier work on static portraiture, drawing and sketching, from about 2005 to 2015, I decided to consider the importance of movement in art making and perceiving, appreciating, cognizing. Danielle being a graffiti artist, we explore that art practice, which is very dependent on movement, and then consider calligraphy as well as writing. More recently, we also work with other groups and start exploring painting. But this, again, could be for another talk. One main hypothesis we identified early on is the following. Informed by prior research in perception and neuroscience, the appreciation of the artifact, in particular the aesthetics, the structures, and the skill, is movement dependent, which is recoverable visually by the observer of a graphical artifact, without physical movement. Here's an illustration of what I mean. Ask your neighbor, how was this made? Most people will have the same or closely similar description of movement, actions, the brush traces. Neuroscience has shown that motor areas of our brain are stimulated by simple observation of such traces. Going back to our focus, we will illustrate results in the dynamics of movement and impact on the quality of the potential calligraphy made. One particular model we've focused on is the sigma log normal model, in particular in collaboration with Professor Régent Palamondon at the University of Montreal, who originally considered limb arm movement when signing, rapid writing, and sketching and drawing. This mathematical model has a number of tricky parameters, and we've done additional work to automatically figure out what are the right parameters for a particular type of action. Here's an illustration of how the sigma log normal model may be useful when considering calligraphy making. You have three targets represented by the red lines on the left. So the same three targets, 3 times. The black traces are the actual movement of the brush, the trace left by a brush. What is different is the kinematics, and the kinematics is illustrated in the middle by the type of sigma log normal function used to capture movement between pair of targets. So you have 2 sigma log normals since there are 3 targets. And you see that when the functions are separated, you can reach the corner very precisely and stop there. So these functions indicate 0 speed at the intermediate point. As soon as you blend the movement modeled by sigma log normal functions, you get smoothing, blending. You cannot reach the corner anymore. And this corresponds well to the action of a human moving rapidly with their trace, leaving trace with their brush. Here's a digital implementation of these ideas, and you see that for the letter M, we can capture believable kinematics, and then we can capture, more importantly, variation. The variations are operating in the kinematics space. Another illustration of the power of using actions or control in the kinematic space is illustrated here by comparing the use of sigma log normal at the top versus typical Bezier splines at the bottom. Very difficult to control Bezier splines, as experts in graphics will tell you. You're operating directly in the geometry space. But if you operate in the movement space, then variations correspond more to how humans behave. Another important contribution of our work in recent years is to produce geometric information which is inspired by knowledge in perception. So here you see what we call the curvy linear shape features, briefly inspired by work by Harry Blum in medial axis representations, by the symmetry curvature duality of Michael Layton and the process grammar. If you're interested, we have publications on this work. Here's finally an illustration of how we can refine the parameters of our sigma log normal models by combining these works. Again, I'm going briefly. We have literature published if you're interested. Re-emphasizing, one of the main power of this approach is to capture variations by acting in the kinematic space, which are believable from a human point of view, correspond well to the type of variation we observe in a human who will have the same idea, same targets, and never do exactly the same type of traces. Once satisfied with the mathematics, with the algorithmic aspects of our modeling, we move on to testing in the physical world with robotics. First, we do simulations in 3D, typical of robotics work, before you go to an actual physical machine. This is work from a few years ago with Dr. Sylvain Callinon, who's an expert in robotics and machine learning. And this system here illustrated can learn from errors. Again, we have publication on this work. Other publications cover different aspects of the research, and I can share with you those details later. I want to emphasize that the work is not just impacting the world of computer science and robotics, but also the world of art, the world of perception in particular. And we have also many exchanges with philosophers of the mind. Towards my conclusion, I want to emphasize now the most recent work we've performed, where we extend the type of robotic calligraphy to other types of creative outcomes. Recently, we published at SIGGRAPH Asia in December this work, which is an attempt to merge together our modeling of the kinematics and the geometric features of shapes, together with modern current neural network approaches, which allow us now to play with constraints coming from different modalities, here illustrated with the image domain. So we have now a way to do calligraphy over image features provided by an image type of input, or it could be a video. Here's another illustration where the initial traces guessed are of very different types, and the image data can be used to converge towards a potentially interesting application of styles corresponding to calligraphic manipulation of brushes. This is exploratory at this point, early steps, shall we say. We also explore the world of LLM, large language models. So this work can be combined with inputs coming from the text modalities. But finally, what's most relevant is the type of movements, the control we can have on modern robots, which corresponds well to human-like movements. Here is with one of our more recent robots, Franca, from a German company. The fact that we have access to these different modalities allows us also to keep exploring sort of creative potential of mixing more traditional aspects of calligraphy with all types of here image domain inputs. To conclude, I want to give you a sense for where the work is going next. So we are now exploring with collaborators in software robotics the world of haptics, the sense of touch, and also proprioception, how you move and feel with your muscles and bones. So when you interact with the brush on a canvas, on paper, on a wall, etc., you have a lot of feelings which influence how you, what you do next in your art practice. So we want to go in that direction and explore this further with collaborators in specialists in robotics. And to summarize, I want to emphasize another main hypothesis, which is the embodiment hypothesis, and that we think of intelligence being at least in part due to and constrained by our body capacities. And this is, I'm thinking more about the dexterity aspect here. Intelligence, hence, can be expressed by actions. Intelligence can be externalized, and this corresponds to this main feature of humans, that we can archive knowledge and pass it on. Many collaborators involved, and I list here some of the main ones. What's noticeable here is that very different domains can collaborate together, including philosophy, psychology, sociology, robotics, and of course computer vision, computer graphics, and visual art. The main current project has been funded, and we thank them, by the AHRC in the UK and by the DFG in Germany. Thank you very much, and I'll be happy to answer questions or discuss aspects of my motivation and the work we do. Here you have one of the emails to reach me, ffl@creativemachine.org.uk. Thanks again.